Hello! In this video, you will get an overview of existing pilot projects and demonstration sites for DC microgrids. For these applications, we will briefly discuss aspects that have been discussed in the course, like the architecture, components, and control and protection methods used. In detail, we will see how DC microgrids have been implemented for different applications, such as off-grid solar systems, transportation, data centers, and residential buildings, and what are the characteristics of each application. Let's start with off-grid DC microgrids. In remote locations where the main AC grid is inaccessible, the DC microgrid needs to operate in a standalone self-sufficient mode. Such application is mostly used in rural areas for households that have no access to electricity, like some states in India or sub-Saharan Africa. An example of such a DC microgrid is the so-called solar home system, which consists typically of a solar panel array for electricity generation, a storage battery bank to supply the loads during the night or in cloudy days, and a DC-DC converter to manage the power flow from the PV array to the battery and the DC loads. In general, solar home systems operate on different voltage levels depending on the load size and range from 12 to 48 volts. The capacity of these systems ranges from around 20 watts in a very small household to 3 kilowatts for a large household or a small community facility such as schools. Commonly, these systems have a radial network topology and a centralized control system. The control system is typically used to monitor the state of charge of the batteries and to protect them during operation. And in cases where the household is connected to the grid, the control system aims to minimize the grid usage and maximize the utilization of energy coming from the PV panels. Another important application where DC microgrids have been implemented is transportation, more specifically electric ships and railway traction systems. All electric DC-based ships have gained interest for commercial design and use, eliminating the use of heavy and bulky transformers and AC switchboards. For example, an existing ship with an onboard DC grid was able to improve its energy efficiency by 20% and reduce the weight of the electrical system by 30%. The ship has an operating voltage level of around 1 kilovolt and a high-capacity power system in order of 10 megawatts. The protection of the onboard grid is usually maintained through a controlled and coordinated use of fuses and isolation switches, as well as protective power electronic devices. The protection and fault can be controlled and stopped within 10 to 20 milliseconds, which is notably faster than what is possible with traditional circuit breakers and protection relays. Let's discuss now railroad vehicles, where historically DC supply has always been preferred over AC. The advantage of DC in this application is the availability of series DC motors, which have high torque and good response to load variation and speed control. We can see in the figure a typical DC traction system with a rail return. Monopolar DC is preferred in this architecture as it simplifies the catenary system. A rail return is used, which is the method usually adopted to reduce costs. But it does present some disadvantages, such as damage to metallic structures and interference with signal circuits. When we look worldwide, the currently used traction systems have an operating voltage from 750 volts for metros and trams to 3 kilovolts for international and regional trains. They have a capacity range of 1.5 to 15 megawatts. A rail return topology is typically used and relies on AC and DC switchgear for fault isolation. Data centers is another application where switching to DC has proven to be beneficial. In 2006, data centers were consuming 1.5% of the United States' total energy consumption. In the figure, we can see the architectures of AC and DC data centers. Having a DC interface between the UPS and the server eliminates the DC to AC and AC to DC losses. For example, the removal of these multiple conversion steps could result in efficiency gains of up to 7%, as with the DC data centers at Lawrence Berkeley National Laboratory. The DC data centers currently operational around the world have an operation voltage level of 380 to 400 volts and have up to 5.5 megawatts power capacity. Many of these data centers have an adaptive control architecture and are protected via suitable low and high voltage DC breakers. The last application of DC microgrids that we're going to discuss in this video is residential DC buildings. As you know, many household appliances like TVs, refrigerators, and computers are DC in nature. Moreover, electric vehicles, which are energy-intensive DC devices, are becoming more and more popular. The nature of these residential loads allows them to be easily connected to DC renewable sources and storage such as PV systems and batteries, making the typical household a DC nanogrid that can be supported by the main grid. This has the potential to eliminate the large number of AC-DC and DC-AC conversion losses that occur in traditional AC households. Moreover, several appliance manufacturers are supporting the modification of products and supplying products that are DC ready, making them easily available for households with DC grids. The control in these grids mainly aims to minimize the energy exchange with the main grid through the use of storage elements, while optimizing the operation of the renewable energy sources and sometimes selling energy to the grid when it's profitable. However, one of the main drawbacks of these household DC grids is the several challenges in protection. This is due to the arcing that occurs more often in these grids due to the relatively high operating voltage, which ranges from 360 and 400 volts, and to the no-zero crossing. Solutions for these are currently being developed. To sum up, in this video, we have seen how DC grids are used to power houses in remote off-grid locations, and how they are becoming more popular and widely used in both the transportation and residential building sectors. With this video, we also conclude the course Integration of Photovoltaic Systems in Microgrids, where you have learned about the basic concepts and different components that make up a microgrid. You are also introduced to the several power electronic interfaces that connect the various distributed generators to the AC and DC feeders and loads. Then, we discussed the various microgrid control concepts, where you saw how hierarchical control is implemented in microgrids. As a final remark regarding this topic, in literature you might find different definitions of primary, secondary, and tertiary control in microgrids. We've added a PDF document that you can use for reference in the Resources and Tools sections of the course, in which the definitions as given by an IEEE task force on microgrids are included. These definitions are in line with our definitions of local, internal, and upstream microgrid control as covered in this course. Additionally, you had an overview over the various protection methods that are used in microgrids and some of their challenges. We finalized with some examples of AC and DC demonstration sites. We hope that you enjoyed taking the course and wish you the best in the exam, but most importantly, applying the concepts that you have learned in your future.